Hi guys, well, the idea of this video is to show you some ideas of how to face the two-dimensional problem with finite differences. We want to think, or we will solve this square I just showed you in the previous video. So I will just show you in a very somehow fundamental way how to face the problem, okay? So we have a square, and I will just write a square maybe like this. So we will have 16 nodes, something like this, for example. So the first thing we have to do is to give some indexing or some labeling to the nodes, okay? So in this class we will also see how we can actually make a vector be expressed in terms of matrices or a matrix in terms of vectors. For example, if we have a two-dimensional matrix like A, B, C, D, we want to somehow convert it into a vector that is composed by A, B, C, D. So this is what I want, what I trying to say when say expressing a matrix into a vector or vice versa. Okay. So in the computational domain, we will only think in these terms. Okay. In order to go from here to here, we have to first then label the nodes. So just let me do this. We will start with 1, 2, 3, 4, and so on. Okay, so we have finished numbering the nodes, and then we have to recognize something in here. These nodes are going to be the ones where the boundary conditions are imposed. These nodes here are the inner nodes, okay? So in this sense, the heat equation is going to be applied to these nodes and the boundary conditions to these nodes. The first thing we will have to do is to do this transformation, okay? I will just do it. Okay, so I have drawn here a matrix vector multiplication. So I have drawn something like this is a matrix A. This is our system of interest. We can call it T, or let's call it X, and this is going to be the right hand side of the question. So this is a classical system AX equal B, okay? And we want to know the unknown, which is X. We are just to have to solve a linear system. Just as a note bypassing, any linear partial differential equation can be expressed in a AX equal B formulation, okay? Because the equation is linear, then you can express it as a linear system of equations. And this is the beauty of linear partial differential equations. Well, what I told you, this is gonna be the T vector, and then we will just start numbering the nodes. 1, 2, 3, 4, 5, and so on. Let's put here 6, 7, 8, and until 16. Okay, this is the first thing. The second thing is to realize that each row in this matrix is going to be associated with the equation of each node. So let me just draw something. Okay, so here I have drawn the lines for just 3 nodes, just to make the example. I have chosen the node 2, node 6, and node 12, but we'll have to do this for every node, okay? Before going beyond, I want just to maybe remind you of something that is quite important. Okay, when you have somehow a dot product, let me just call it here. This is going to be A1, A2, A3. This is an example, and this is another thing. Let's call it I don't know, B. No. Let's put it X, X1, X2, X3. So this is like the column and the row in this example. Okay. What does it mean? It means that you are multiplying A1 times X1 plus A2 times X2 plus A3 times X3. Okay, so this is the example, which means that what we're doing in here is to have this column, which is T1, T2, T3, T4, T5 until T6, multiply by each element in here. Okay, and this is how we will introduce the equations that we're interested in. Okay, so to start, let me just draw or write a very simple equation. So the most simple equation is the equation at the boundaries. Oh, here is something happened. I have to write again here 1, 1, 2, 3, 4. Okay. So we will start imposing the Dirichlet boundary condition. This is the simple equation, the most simple equation. And let's assume, this is because I'm designing the problem. I assume that these nodes in here we will have this Dirichlet boundary condition, which means that I'm already imposing a given value of the temperature. So I will say I want that all this wall, so this wall is gonna be just given or impose, I don't know, 100 Celsius. Okay, so we will know that T1 is equal to 100, T2, and all these T3, T4, all of them are going to be given this number 100. Okay, and if we go back to the previous example of this dot product or vector multiplication, it's like imposing something like this: 1, 0, 0. Okay, and then a given temperature in here, 1, 2, and so on, and then the corresponding value of the temperature, which is going to be 100. Okay, so this is what we want to do, and I will just write it in the actual metrics. So in this case we have the example of only the node 2, so we will just consider this node 2, and we have the first is going to be just 0, the second is going to be 1, because 1 is going to multiply T2. This is the vector T, remember, so this is going to be 1, and the rest are going to be 0. Okay, so this is 0, and voila, you have there the equation for the node 2. Now let's go, for example, and apply now the actual equation to the inner nodes. So again, every node has a equation, and the inner nodes are the ones who have the equation that we want to solve, which is the heat equation. The other nodes, the boundary, they have the equations of the boundaries, so the boundary conditions. So I will not tell you this one. So this is going to be in this exercise, if you remember, this is going to be Neumann, this is going to be Robin, this is going to be Robin as well. Now let's concentrate on these ones. Also, because this is part of the exercise that you derive the stencil of the second order derivative of the heat equation. In this example right now, I will just invent an equation, okay? Just to give you an idea of what I want to say. So I will just invent an equation. So the question for the inner nodes is a given relation, remember, linear combination of the nodes that are at the east, at the west, at the north, at the south, and so on. Okay, so the question, this is completely just, I'm just inventing it right now. You just have, for example, yeah, it's 3p tp plus 2t south plus 3, no, maybe 4 t north plus 2t east equals 0. This is t east. So that's the question. This is just an example to show you how to express this equation in this matrix vector multiplication. Okay, so this is not the heat equation. I just want to be you to be clear. Okay, so what do we do now? The idea is that we will somehow apply this equation to the inner nodes. So we have 6, 10, 7, and 11. These are the inner nodes. Okay, but then we have to translate this equation for each node. So, okay, so just let me erase this. And I will just write the equation. So this equation is going to be, now let's go node 6. Node 6, what is 3 and what is TP? So we are standing at 6, therefore TP is T6. Then plus 2 south, and we see here the south of 6 is 7. Then we will do plus 2T7 plus 4T north, therefore we have 4. And what is at the north of 6? Yeah, it's T5 plus 2, and then at the east of 6, T10. And this is equal to 0. Okay, so this is the equation. For T7, it changes, no? I mean, I want just to be sure. So let's do it for T7 quickly. So it's gonna be 3T7 plus 2 times T8 plus 4 times, this is what? North is 6 plus 2 times at the east T11. Okay, and so on. So this is the equation, or how it should be written for each node, and so on. So if we want to express this in this matrix, then we will start and we will say, okay, there is nothing multiplying T1, therefore the first one is 0. The second one is nothing multiplying T2, 0. Okay, actually I can do that until 5. So 0, 0, and the first one is actually 5, T5. If you see here, T5 is happening in here. Now we have something to multiply to, so this is gonna be 4. Then we will continue. 6 is going to be 3. Then 7 is going to be 2. Then 8 there is nothing. 9 there is nothing. 10 we have 2, and there is nothing in the rest. Okay, and then we have actually built the equation for node 6. So the idea is that you will do that for every single node, and at the end you will fill this matrix A. When you fill the matrix A, then you just have to solve the linear system of equations. Use the Bash-Lag operator, so you can write it something like x is equal to a Bash-Lag operator b, and then you will have the answer. Okay, When you have the answer, then you have to go back from this vector, not the, so from this vector that in this case is 1 to 6, so 16 rows, 1 column, to a 4 times 4 matrix, and then you display the results, and that's all. Okay, so you can see here that this is a concept that is interesting, that is important to point out, is the difference between what we call the physical matrix. So the physical matrix is 4 times 4. The computational matrix is not 4 times 4, is 16 times 16. And this is an example of just some few nodes, okay? And just to be sure that I'm trying to be general, I mean the computational matrix doesn't have to be a square, okay? In finite differences, we can have, for example, rectangles. So we could have 4 times 3, and the computational matrix would be 12 times 12. Basically, when we go to finite volumes, you will see that we can actually have things that do not are actually cuboids or squares. They are much more like free. I mean, nothing really standard. So the physical matrix is going to be something like it's not really defined, but the computational matrix is going to be always a square, okay, because it's an equation per node. Okay, and two final remarks. One remark is you could start doing the exercise, and I actually suggested maybe with this 4 times 4 matrix, and just to understand the concept and the implementation of the actual heat equation. Remember that this is not the heat equation. You have to derive the heat equation, the stencil, the discretized equation, and put it in the matrix for every row of the inner nodes. So I suggest we start with a brute force. So we do it by hand. We actually get the whole procedure in a very somehow hard way, because we do it somehow by hand, and we solve the system of equations, okay, with the Batch-Lac operator, and we get some results. But it's gonna be a very coarse mesh. It's gonna be just a 4 times 4 matrix. Okay. So the next step, when you get things working already, and you get the idea, the flavor of what we're talking about, the exercise, the finite differences, discretization, then in that moment you say, okay, now let's be smart. And then you will try, I will not give you a hint, because that's gonna be, it will be like very chatty, it will be very not fun. Okay, think how to do this, to put the equation at every node in a smart way, so that if I can tell you, okay, solve this equation for a matrix 50 times 50 or 90 times 200 or something like that, that you are able to do that just by changing two lines at the beginning of your code, and that the code itself is able to fill the lines already with the corresponding equation. Okay, so this is something I don't want to tell you, so I really prefer that you think and have fun trying to somehow solve this problem. So this is one comment. Okay, so first start easy, start just doing something in a very dual way, just writing by hand, and once you have things working for a small matrix, then you just try to be as smart as possible and derive a method, just making some coding to find this somehow automatized filling of the rows. This is one thing. The other question comes is how to, when you have the result, how to plot it. Remember that you will get here an x, and this x is gonna be a column. In this example, it's gonna be one column, 16 rows, and then you transform into 4 times 4. So in that moment, you will use a surface plot and contour plot, p-color plot, something that plots you something like surfaces, and then you will introduce. You need 3 arguments. You need the x, y, and the corresponding value. So it just give me I just type it. So this is what I meant, to have x, y_t. This is the command to plot the results in MATLAB. So this is, in this example, the 4 times 4 matrix, and this is going to be like a sort of coordinates of the mesh. Okay, these coordinates right now we can just simply use mesh grid, and you can create this with mesh grid. Okay, so this is before, and when you have this, then you just get these x and y matrices to plot the whole temperature field. Okay, we will keep connected anyway the whole day, and I will be answering your questions. You will be also working in clusters, so you have people to that will support you. I mean, you all support each other, and well, having fun is the most important thing today. Okay, so let's see how everything goes. Bye bye.